So first off, I want to welcome everybody here. Thank you for coming to the webinar today. I guess this is about our fourth IAFSM webinar. And this particular one is special because we pretty much only invited IAFSM people. And typically we've kept them open to other agencies and other basically the public, just so that everybody could get a sense for what the IAFSM was doing. And but this time we closed the doors a little bit, and this is going to be specific to our members. And hopefully this presentation will let you see some of the things you can do in CloudCompare and give you some value. So our presenter today is Daniel Girardon-Monteau. Hopefully I said that correctly. Okay, good. And Daniel is from France. He's 34 years old, a French engineer. He was from École de Mines, which has nothing to do with mines, he tells me anymore. But he has a PhD in signal and image processing, and he's currently working for a computer-assisted surgery company. And he also has developed CloudCompare, and this was an independent project of his. I have used it now for, I would say, about a year, and on and off. And this program has really grown. It has really changed. And about every 2 or 3 months, there are some new updates and new features. Daniel has been excellent about putting in some really good quality features in his program. And this particular program is free, and that means that everybody can pull some value out of it. And I think after the presentation, hopefully you'll see that there's some really good value out of this. So on that note, I will pass it over to Daniel, and the only other thing that I will say is we're going to try to address everybody's questions. If you type it into the little chat window, we'll try to keep a record. Daniel, if the question is sort of in line with what you're talking about, I may interrupt you and just jump in if that's okay. Otherwise, we'll try to get to everybody's questions at the end.
Okay.
All right. Thanks, Daniel. Go ahead.
Thank you very much, Eugene, and hi everyone. Sorry for the being a little late. So of course, first I wish to thank Eugene for giving me the opportunity to present you the CloudCompare project. Can you see I assume you see my screen?
Yes.
Must be okay. Very good. So I'll start my presentation with some background on the project about its genesis. I'll go very quickly over some very general stuff like the user interface and such things. Afterwards, I'll speak more deeply about the typical application of CloudCompare, which is a comparison, how to compare two point clouds typically, and what are the different steps involved. And eventually, of course, I'll speak about the analysis and display of the results. So, did you get all that well?
Yeah, Daniel, that's good. I'm muting my line so I don't make any noise. So if I'm a little slow to respond, it's only because I'm on
okay.
mute. Yeah, everything's coming in fine.
Okay, I just want to check that the sound is okay. So the project started during my PhD. My PhD studies started in 2003, and it was financed by EDF R&D. EDF is the French electric utility. This is a quite big company, more than 100,000 employees, and it handles more than 50 nuclear reactors. And for the little story, they owned at that time Mency, the laser scanner manufacturer, and a few times after that they sold it to Trimble, and this is now Trimble 3D laser scanning. So anyway, EDF was very interested and involved in everything that dealt with laser scanning. My PhD subject was change detection on 3D data, and of course we were thinking about laser scanning data, huge data sets, and sadly the inspiration for this subject was the recovery efforts after the 9/11 tragedy. I've been quite impressed by what Optech did at that time with a laser scanner. They brought a laser scanner on the ground zero area and made lots of measurements, mainly for several purposes like visualization, but also subsidence monitoring. So it was a really interesting work, even in tragic conditions. So we wanted to follow up. So the CloudCompare software itself started just years after that. Its initial goals were to compare relatively big point clouds coming from laser scanners, and in order to quickly assess for changes, it was important to do it quickly, either in case of emergency, or also simply for the topographers to get almost real-time feedback on the field. And the other main goal was to avoid the necessity of computing a mesh structure on top of the point cloud, which is a very hard process. And we thought at that time that the cloud density, especially for laser scanners, was the key for the success. So this is all where CloudCompare come from. Only using clouds and doing everything quite quickly. And since then, it has evolved a lot, as Eugene said, and especially it's open source now since 2010, and it has much more methods than simply comparing a point cloud. It's a more general multi-purpose point cloud editing and processing software today. So the user interface is quite yeah.
Sorry, just a very quick thing. Somebody made a comment that not only do you have CloudCompare, you also have a viewer, and the viewer is available to load up point clouds, and you can show people or they can manipulate. One comment that this was from Wes Grimes in Arizona was that it would be nice to have ability to measure in the viewer.
Oh, directly in the viewer?
Yeah. But anyway, it's just a comment, but I think it's important to know that you have CloudCompare, but you also have the viewer.
Yeah, I talk about that at the end of the presentation, but indeed, you're right.
Okay, good.
So now I mainly focus on CloudCompare for this presentation. So the graphical user interface is quite common. You have one or several 3D views. I'm not sure everyone knows that you can create as many 3D views as you want. Anyway, you have also a database view, and if you select an entity in this view, you get access to its properties. There's lots of them, and you can modify them. It's quite general. You've got a lot of menus and toolbars to get access to the most common tools. And there's also a toolbar on the left dedicated to the 3D views. And last but not least, you have a console at the bottom of the screen where CloudCompare will display most of its results and information or even errors, sadly. About the input and output, we mainly handle point cloud files and triangular meshes, only standard formats. Sadly, we can't. We don't have access to manufacturers' formats. They don't like to share the format specifications, for instance. So we are stuck with open formats, and we have a dedicated format which is called bin for binary, and it's quite useful because you can save any kind of entity, clouds, meshes, labels, even viewports, and you can save in a single file. So this is the best way to save ongoing projects, for instance. We also handle more exotic formats like calibrated pictures coming from the bundler tool, and also a CAD format, but which is quite well. You won't meet this kind of format very often, as it's merely used in the power plant industry. And I hope we'll be able to ship soon new version with new formats, especially shapefiles and the AutoCAD open format, mainly to export polylines and polygons to AutoCAD or GIS software, for instance. So now let's step in the main, the heart of CloudCompare, which is the comparison application. I will detail the workflow, the typical workflow. You generally have at least two clouds of the entities you want to compare. They may not be in the same coordinate system. They may even not have the same scale. So the very first step is generally registration. You generally also have to clean at least one of the clouds, especially the reference one, to get a good an accurate result without too much noise. And also, and sadly, you have to repeat this process iteratively. Once you are done with that, you may want to apply other processing like subsampling or meshing. And at the end, when you're ready, you can perform distances computation and eventually analysis and display. So, registration, you must all know that it's quite a difficult task. It's almost impossible to do it automatically. And as I said, it's generally an iterative process, starting from very coarse methods to finer but also generally slower approaches. So I'll show you only PowerPoint slides for the moment. I'll show you about every method that you can use for the registration and the cleaning process, and then I'll make a real-time demo, which I think will be much clearer than this presentation. So the first step, the simplest one, is simply to make both cloud centers coincide in space. We have a very simple tool which is named Synchronize. You just have to click on both entities, click and synchronize, and CloudCompare will make their centers coincide in space. So this is just only a first step, obviously. Then you can interactively manipulate the clouds, rotate it and translate it with the graphical transformation tool, which corresponds to the red arrows icon. When you launch this tool, you must select only the cloud that you want to move. Then you can interactively rotate it and translate it. You can also apply constraints on the rotation and translation, but it's clearly a quite painful process. So generally you won't use that for a proper registration process. You'll prefer the point pairs based alignment tool, for instance, which is a tool that lets you pick several pairs of points. Each pair of points is composed of one equivalent point, one point in each cloud that are equivalent. You must select at least 3 pairs, but you'll generally need more of them to get an accurate result. And once you have the pairs selected, you just have to align, make CloudCompare compute the alignment matrix, and you'll get a quite nice result. And the last solution, which is generally the most accurate, but which is also hard to tame, is the ICP algorithm. It only works with clouds already roughly registered, and even more than roughly registered. You have to get the clouds very close before calling this tool. And the most problematic thing is that it is designed, it is meant to be used with exactly the same object in theory. So if you have structural differences between your clouds, it will be more problematic, but we have some solutions in CloudCompare. And indeed, this is what this slide is about. What can I do if my entities have structural differences? As I just said, if it is small local differences, you'll only have issues with ICP. But we have a solution. I'll speak of it during my real-time demo, I think. It will be easier to understand. And if the clouds have different scales, there is the appropriate checkbox in both the ICP tool and the point pair-based alignment tool. And if it's major differences, if both clouds have almost nothing in common, you are bound to use the point pair-based alignment tool. The ICP won't do. And eventually, you can do almost the same thing if you have if one of your entities is a mesh. But, and it's more general in CloudCompare, all algorithms don't accept meshes as inputs. So you generally have to sample points on one of the mesh. There's a method dedicated to that, which lets you sample as many points as you want on the mesh. Then you use this sampled cloud for the different processes. And for instance, for the registration algorithms, you simply have to take the resulting transformation and apply it back on the mesh. It's a bit of hacking. It's not very pleasant, I know, but we'll speak of it again later. CloudCompare is not meant to be used with meshes. So that's it. Yeah.
I have a quick question. So if you have 2 point clouds which share some common features, and whether it's, let's say it's a roadway or could be part of a house or a building, whatever, but then there's a significant portion which is different, it's also possible to segment the part that is different. So basically cut it out and then register the 2 parts that are similar and then apply the transformation to the part that's been segmented.
Oh, yes. It's a very good remark. Exactly. You can do that as well. This is a bit of a trick, but this is perfectly right. And it's definitely a good idea when if the subsets of the cloud that you segment and that you register. After that, it must be, there must be edges, and it must not be too flat for the ICP to converge. Yeah. And so, and to finish about the registration of a mesh with the cloud, for the ICP process, you can directly use the mesh, but it's generally a good idea to use it as the reference, because meshes are less old and generally no noise. About cleaning, which is the other, generally the other process that you'll have to iteratively apply. There's also various methods. The first one, once again, is to perform manual editing. You can select the points to remove. There's also a quick and simple tool which is called connected components labeling, which lets you, which will automatically split the clouds in several components. It's very useful to remove isolated parts. And there are several other methods to remove isolated points or the noise or noisy points, either by segmenting the points based on their associated value. In fact, CloudCompare is able to compute a lot of measures on points. It can be the distances, but it can be also the roughness or the density, for instance. And you can, in a generic way, segment those points based on their associated value. So if you want to remove the points with a too low density, it's one of the ways to remove isolated points, for instance. And there's also another way to remove noise with the QPTL plugin, which is this plugin is a simple bridge to the quite well-known PCL library, which has a lot of point cloud processing algorithms. So sadly, we don't give access to all of them. There's too many. But one of them is quite interesting. It's called SOR, for statistical outliers removal, and it's quite powerful for removing noise. So yes, to end this part, you may also want, before computing the distances, you may want to subsample the clouds if it's too big, for instance. And there's a dedicated tool. And you may also want, especially if you have big holes, you may want to compute a mesh. So there's a very simple approaches in CloudCompare. Either 2D and half, as we say, algorithm. It simply means that your cloud must be almost flat for it to work well. And there's also the Poisson reconstruction plugin, which will try to compute a mesh, but it only works on closed clouds and closed shapes. And I must warn you that CloudCompare is not a meshing tool. Far from it, in fact. Remember that at the very beginning of the project, our aim was to avoid computing mesh. So we only provide those two tools above for convenience, and if you need accurate results, you should really consider using a true meshing tool. There's lots of them, even if it's clear that computing a mesh is quite hard, especially a clean mesh. But this issue is not addressed in CloudCompare. So before talking about distances computation, I'd like to show you a real-time demonstration.
Daniel, sorry.
Yeah.
Daniel, sorry to interrupt for a second. I just want to make note of the time because it's about 10:36 here, and I know that maybe some people have to leave at 11. So I'm not trying to rush you too much because I know we started late, but I just want you to be aware of the time. Yeah.
Okay. I'll go quickly on the demo. So you can see that it has been involved in a car accident, obviously. I'm not sure if it's easy for you to see. We directly use the connected components labeling tool as a demonstration. So this is this icon. Sorry about that, but it's true that the first parameter is totally unclear. It corresponds to the subdivision level of the octree that is used by the algorithm. In the near future, I will change that so that the user will just have to give a minimum space between the components. It will be much clearer, but for the moment we'll use it as is. So we don't see very much. In fact, CloudCompare has created several components. Let me select them. Yeah. I hope that you can see that the cloud has been subdivided in several parts. The biggest one is the car hull itself. It's the one we want to keep. And the other one, I'm not sure if you can see them clearly, are the small isolated parts that we are going to remove.
Yeah, we can see them here. They look we can see it pretty clear.
Okay, good. So we only keep the main hull. We see that there are still quite a lot of noise. So just for the demonstration, I quickly remove them manually with the segment tool, the size of the icon. You just have to draw a polyline on screen, and then you choose either to remove the points inside the polygon or outside. So in this case, I keep the points outside. You can repeat the process several times. You just have to unpause the tool, draw your polygon, and then choose to keep the points outside, and so on until you are done. And once you are done, you can either confirm the segmentation with the green symbol, in which case CloudCompare will create two clouds, one with the points currently visible and one with the discarded points. You only keep the selected points. So let's say we have cleaned successfully both clouds to go faster. So now we want to register them. First step, as I said, is to make them closer with the synchronize tool. Okay. I could, of course, rotate manually the car, but that's not the point here, and it's never as accurate as we'd like to be. So I'm not going to do that. I'm going to make a demo of the point pair based alignment tool. So this is this icon. For this kind of tool, you always have to choose which cloud will be the reference and which cloud will be the align cloud or the data cloud. It depends on the tool, but it's just to let CloudCompare know what cloud is should move and which cloud should stay T-Mobile. So this tool, Eugene has already shipped out a great tutorial video about this. So I go quickly. You just have to select several points in the same point in both clouds in the same order. You can show only one cloud at a time. It's generally easier. So I start with the blue one. Let me select quite easy points. Generally at sharp edges, and this one, for instance, and this one, it's just for the demonstration, so I don't need the great accuracy. Let me select the same points in the black car. Almost. Anyway, the cars are not the same, so we can't achieve a great registration accuracy. But so when I've finished picking my points, I just have to click. I can show both of them. I click on Align, and you see that both have been registered. It may have gone too fast. Well, you see the RMS error, root mean square, which is quite good for two cars that are quite different, below 5 centimeters here. And of course, you can repeat the process. You can add pairs of points if you want to get a more accurate or more robust result. You can also input manual points, which is quite useful if you have a total station, for instance. Anyway, once you're done, you just have to confirm. CloudCompare will display a small report, and you'll get the same information, in fact, in the console, which is the final RMS, the corresponding transformation matrix. We don't have changed the scale, but we could have told CloudCompare that the scale was not the same. It would have make both cloud fit. Anyway, we are done for this part. So we see that both cards are much better registered now. Yes, I think I'm gonna also show you the ICP process. Even if it's not quite a good idea here, as the cars are quite different. So once again, you have to select which one will be the reference, which in the ICP vocabulary is named model, and so this is the good one, and the data cloud is the one that will move. So the automatic selection is already good. You can select the final error difference. Generally, leaving the default value is good. And for the scale, we will let the scale of the data cloud, the moving cloud, change, as it's not exactly the same car. It's a good idea, I think. And we'll also enable this option, which is enable farthest point removal, and which is basically a way to tell CloudCompare to ignore the farthest points at each iteration more and more, so that the bigger differences don't interfere with the registration process, and it lets the ICP process converge much better. So the ICP process is ongoing. It's generally quite fast. You see, it worked pretty well, in fact, even if the cars are not exactly the same. The scale has almost not changed, and the resulting RMS is now below 4 centimeters, which is quite good. Okay, so let's say we have successfully registered both clouds, and we can consider they are clean enough. So now we will compute the distances. So I'm going to show you right away how it looks like, and then I'll explain you a bit more about the theory behind it. So to compute the distances, you just have to select both clouds. Click on this icon, which is compute cloud-to-cloud distance. You can find all these tools also in the tools menu under the registration and distances submenu. So once again, you have to choose between which cloud will be the reference and which one will be the compared cloud. So here I have to invert them. This is the Mazda, which is the reference. First, CloudCompare will perform a very approximate distance computation. It's only for it to be able to set parameters, quite tricky parameters that the user won't be able to set itself. You can also apply some more parameters like local modeling. I'll talk about this later during my presentation. Anyway, generally, you just have to compute, to click on the compute button. The computation time is really highly depends on the number of points, of course, but also the extent of the clouds. So in this case, it's quite fast. Okay, it's down. We can now hide the reference cloud, and you see the results on the black car. Each point is colored with its depending on its distance to the reference car. One thing that is very interesting, of course, is to display the associated color scale. You can change the precision of the digits. We don't need 6 digits here, only 3, and I'll make the font bigger for you. And when you're here, you're able to perform lots of actions. You can spawn labels. You just have to hold the Shift key and click on a point. This will let you see, for instance, the distance of this particular point. You can also edit the color scale. This is a quite new tool, which is called the Color Scale Manager, I think. Just next to the color scale selector, you can click on this, and you can edit the colors. This one is read-only, as we say. It's moreover, it's a relative color scale, so it means that the color scale automatically spans between the minimum and the maximum distance, which is generally not a good idea. So you'll typically want to create your own color bar when you're at this point. So you just have to copy the original one, make it absolute. So I won't enter into too much details here, but it lets you say that the color are only associated to a given distance. So let's say between 1 and 0.5 meters, I think it's meters. The yellow at 0.2 and the green at 0.1. It's just you can rename the scale, of course. Let's say 15 centimeters, 50 centimeters. Save it and apply. So now CloudCompare will use this color scale. And this color scale is absolute, which is quite interesting, especially if I want to make a sub-selection, a particular selection of points. For instance, if I'm only interested in the areas with with high deformations, I select, for instance, only the points above maybe 40 centimeters. I can first tell CloudCompare not to show me those points if I only want to focus on the areas with high distances. And I can even ask CloudCompare to create a new cloud with only those points. There's a method named filter points by value. You can enter the boundaries, any boundaries you want, but by default it will take the display boundaries. So this is exactly what we want. So CloudCompare has created a new cloud. For this new cloud, we must display again its color scale, as it's not the same cloud. And here we are. I think, of course, you can display a histogram of the distances, which can be quite useful. You can create more labels. You can you can also measure distances. I might have been quite too quick here. There's a point picking tool on the upper left part of the main toolbar, which lets you pick multiple points, either for measuring distances. You can save it, for instance. You shoot it each time you create a new label. You can even create a rectangular selection. For instance, front wheel. And last but not least, you can save, as I said earlier, the viewports. In the display menu, there's a save viewport as object. It will create a new object called viewport that remember the current camera position. So if you change manually the parameters of the camera, you can ask the respawn the old viewport. So this is a good way to save a whole project. You save, of course, the compared cloud, the corresponding labels, and the viewports. You can save all of these entities in a single bin file, and you'll be able to reload it later with exactly the same position. So now I'll get back to the PowerPoint presentation. I'll try not to go too deeply, but I'll still go a little deeper in the theory of distances computation. So generally, when you compute the distances between two clouds, in fact, you compute the distances between every point of the compared cloud to the nearest point in the reference cloud. Yes, there's a small demonstration here. You can see. And one important thing is that the process is not symmetrical. So when you want to compute distances in CloudCompare, there's two real cases. Either you compare two clouds, just as I presented you. Either you can compare one cloud and a mesh. There's a dedicated method for that. And if you want to compare two meshes, the only way for now in CloudCompare is, as I told earlier, to sample points on one of the mesh, especially the compared mesh, and then you'll perform, in fact, the comparison between a cloud and a mesh. About the cloud-to-cloud distances, so as I told during the introduction, the main idea was to avoid computing a mesh. And the idea is that if the cloud is the reference cloud is dense enough, computing the distance between the reference cloud and this dense reference cloud is almost as accurate as computing the distance between the compared cloud and the true underlying surface represented by the reference cloud. The theory tells us that the error is bounded in this case, and it only depends on the reference cloud density. So sorry for the maths. I only wanted to show you this curve because this is the distance, the distribution of distances in a random Poisson process. It simply means that if you sample points randomly on a surface and then you look at their relative distance, depending on the density, most of the points will be at a given distance, and you'll get much fewer points at lower or higher distances. And try to remember of the shape of this distribution, because I show an interesting result later. As a consequence, and this is a very general remark, you should always use the denser cloud as a reference, of course, if it's possible. As you'll get a much lower error if you use the denser cloud as reference, and you don't need high density for the compared cloud. And of course, the reference cloud should always be as large, at least, as the compared one. You really have to avoid non-overlapping areas, or you'll get high distances, which in fact don't correspond to any true difference. So, to end this small talk about theory, let's say that we want to compute the distance between the point P and the surface, here, sigma, which is only described by a few points. So when we compute the nearest neighbor distance, as we do in CloudCompare, we make a small error relatively to the true distance. So here is an example, and you see that the distribution of distances, even if it's with real data sets, it's quite exactly the same shape as the Poisson distribution. So we can say that we really are close to the theory here. The laser scanners really behave like a Poisson process. It's quite interesting. So to cope with this issue, with the fact that we always make an error depending on the density, there's an option in CloudCompare when you compute the distances to apply a local model. Instead of computing simply the distance between the point and its nearest neighbor and the other cloud, we consider a small neighborhood around the nearest neighbor. We apply a very simple model, like it can be the best fitting least squares plane or the 2D Delaunay triangulation. Very simple, only local, and you compute then the distance between the point and its model, and you by this way you lower the error quite much, in fact, in general. So here is on the same dataset with one of the local meshing strategy, and you see that the error distribution is much nicer, in fact, much closer to zero, which was the true error for most of those points. So this is a nice feature. It's just a bit slower to compute, and it's important to know that the result is only valid for in a global understanding. I'm not sure if it's clear. It's only a statistical result. You get better results on the whole cloud. Locally, you can have worse results, but if you want to consider the global distances distribution, it's generally much better. But you only have to take that into account and to use this local meshing strategy if you need really high accuracy and if your cloud is not dense enough. So I've already shown you the cloud-to-cloud distance tool. There's the same tool for computing the distance between a cloud and a mesh. If you have a very clean mesh, it's generally a good idea to use the mesh as the reference, as it's much cleaner and much more accurate. We compute the distance between each point of the cloud and its nearest triangle in the mesh. So there's no issue with the density, the reference density, for instance. It's quite fast also. And the main difference, yes, is that you'll get signed distances, meaning the distances can be plus or minus zero, because the mesh gives us an information about the orientation of the surface. Are we inside or outside the object? So this is also more interesting. But of course, it's not always possible to get a clean mesh. As an example, I've shown you a very classic example for CloudCompare, which is the difference between a point cloud acquired in a power plant facility and the theoretical CAD geometry. So it works pretty the same as the cloud-to-cloud distance. You just do the same options, and you get a signed result. Here you see that the distances can be either negative or positive, which is quite nice. But the result is globally the same, and you can apply exactly the same process afterward. And to finish my presentation, I'll very quickly talk about analysis and display. As I've shown you, once you get the distance field, you can display histogram. There's a quite tricky tool which is named local statistical testing, which is a bit hard to tame also, but which lets you know if you know quite accurately the noise of your measuring process, and you really need to achieve a very good accuracy on the distance computation and the distance computation results. You can try with this tool to classify the points between those that have non-zero distances but who are in fact only corresponding to noise, and the points that are really corresponding to differences. But I won't talk much about it because it's quite complicated to use, and its parameters are not easy to understand. Don't hesitate to ask me about it later by mail, for instance. And one also good way to get more results about this distance field is to export it as a text format, ASCII, to export it, for instance, to MATLAB or Excel. As you saw before, you can create a label, save your viewports, save the whole project as a bin file. And as Eugene told, there's also a CC viewer which is a very lightweight viewer-only application based on CloudCompare, which can be used for to load and display clouds. Here is an example with a nice cloud provided by Eugene. So CC Viewer is much simpler. You can only drag and drop files in its unique 3D view, and it will load it. And there's very few options so as to be as simple as possible. So thank you for your attention, and I hope you did get everything I told, and don't hesitate to ask me a question.
Daniel, I have one thing before, and I think it's a very useful tool. In the subsampling, could you quickly show how you can subsample one of the cars maybe from a space limited? Because, for a lot of people, when you scan, the points closer to the scanner can be very, very dense, and maybe you don't need that kind of density. And so I found this to be a very useful tool for lightening the point count, but still keeping the density where you need it.
Yeah, indeed, and especially all my talk about the cloud, the reference cloud density it's also a problem if you have a reference cloud with a density which is very different from one point to another, as you won't make the same errors on the measures depending on where you are in the cloud. So you also it's also a good idea to subsample the cloud for this reason. So the subsample cloud is correspond to this icon, the blue and red dots. You can find it also in the edit menu, edit subsample. Then you have three choices. Either you randomly select a given number of points, quite easy to understand. It won't change, however, the relative differences of density between the points. So what interests you more is the space method, which will guarantee that you won't have 2 points closer than the space that the length that you define here. So just to be clear, if for instance, I will ask CloudCompare to remove any points closer to 1 centimeter here, 10 centimeter. So here, let me test this. Okay, so I'm not sure if you have clearly seen the difference. I can switch between the two clouds. Hop. So that
the new cloud looks like it's about 2 million points just over, and the previous one?
Yeah, now the new one is 191.
Okay,
yeah. It's 10% of the original one. It's of course much easier to handle, and it should have a much better density. How can you say that? Repartition.
Right.
So indeed, it's quite a very interesting tool.
There was a question, Daniel, about the when you have the color scale, the height ramp on the right side. It looks like there's to the right of the bar. There looks like there's a little histogram there as well. Is that true?
Oh yeah, exactly. It's one of the newest feature. The color bar has changed a lot since the last version, and this is exactly it. You get the histogram, the same histogram that you can see if you select the right cloud, of course. Here it is. Oh no, it's not exactly the same, but I don't know which cloud selected. This one. Okay, here it is. So you've got, even if it's hard to see like that, you've got the same histogram.
Okay. And what you can change the classes and such in there. What does that do?
Oh, for the histogram, yes, you can set as many classes as you want. Depends on the accuracy you want to for your histogram display.
Okay, so it breaks it down into groups basically.
Yeah, exactly. It's generally useful to change it if you have how do you say that? If you have sampling issues with distances that would be too regularly sampled. For instance, if you have distances with only integer values like 1, 2, 3, 4, and when you compute the histogram, you can have very strange sampling issues, effects. So it's quite handy to change that, but generally you don't have to change it.
Okay. Are there any other plugins, Daniel, that are available for CloudCompare that don't come packaged with it already?
There are plugins, but which are not public yet. In fact, some companies I know have developed their own plugins, but they are not obliged to share them as long as it stays by them in a private circle, I would say. So I'm trying to make them redistribute the plugins, but it always takes some time. And you will see I hope in about a year, new plugins indeed.
Okay. Anyone else that has other questions? You drop them in the chat window now if you like. Well, we're getting close to the time, so I don't see any other questions at the moment. But Daniel, oh wait. Somebody has a question about import and export capabilities. That's a good point. Maybe just very quickly show how you can export a point cloud and what kind of things you can import.
Yeah. So I think the most interesting tool about feature about importing is when you try to import ASCII text clouds, like PTS format, for instance. Let me find some views, for instance. Let's go. So when you try to load an ASCII text point cloud like PTS, you will get this wizard, which lets you assign each column of values to a particular role, for instance, X, Y, and Z coordinates, and red, green, blue. There's lots of other properties like normal, scalar fit, of course, particular colors. So of course you can change that as you wish. You can ignore some columns, and it lets you choose. You can also swap the values. You'll get quite strange results, but let's try it. And you can also, it's quite nice, you can choose the maximum number of points per cloud, because the old 32-bit version of CloudCompare was limited to a little bit more than 100 million points, I think. But the new 64-bit version is no more limited. But you could be interested in keeping the same limits, in which case CloudCompare will split the cloud in several parts automatically. So anyway, afterwards you can import the cloud. Yes, you see the inverted colors. You can also invert the coordinates. This is more useful generally. And when you want to export entities, if it's a single entity, for instance, I simply selected this cloud. You can click on the floppy icon, which will display the save dialog, and you can choose between several formats. The format displayed here depends on the entity you have selected, either a mesh or a cloud mainly. And if you select multiple clouds, you'll generally only see the pin CloudCompare format, which is one of the few that is able to save multiple types of entities mixed together. And for the formats, as I said, we have mainly classical open formats like ASCII text files, E57, and PLY, which is a Stanford format, which is generally used for meshes, but which also works for cloud. VTK, which is a common medical imaging format library. LAS, of course, and the two other formats are very particular and old, and no one uses them. But anyway, don't forget when you save, especially a bin file, to select all the clouds that you need and all the items, even the viewports, for instance, and the labels. Otherwise, they won't be saved in the file.
Okay. Okay, another question. In the measurement window, before when you click on a point, it shows, for example, X, Y, Z coordinates. It also provides a point number as well. And somebody's asking, is that I'm not sure. Is the point number one of the available records for the point? That's from Chris. Not sure if
the measurement window.
Oh, does the point number get exported? I guess is what he's asking.
Oh. When you save as ASCII, maybe?
I don't know.
No. I'm not sure about the dialog.
Okay. I don't think so. So I don't think it saves the point number.
Oh, yes, sorry.
CSV?
Sorry, of course. How could I forgot about that? Indeed, if you save as an ASCII file, you've also got a new dialog, which lets you choose the coordinates precision, the scalar field precision. You may not want exactly the same. The separator, of course, if you want to import that in Excel, you will prefer the comma or the semicolon, for instance.
Okay.
The order is quite important for PTS files, I think. I don't remember which software needs a particular order, requires a particular order. And eventually, you can check those two checkboxes. The first will write a small header with the name of each column. And especially, it's a good way to save the scalar field names. And the other one, indeed, is will make CloudCompare save in the very first line of the file the number of points that are going to be saved. It's also very important for some software and in the PTS format, I think.
Okay. Just another question or two, and I think then we're going to call it quits here. One question came up is, can you name a point so that it can be referenced between scans? So, for example, if you pick a point and give it a specific name in one scan, and then pick the same point in another scan, and then somehow it will reference the two. I think that's kind of like the point picking, but it's not, but it's. I guess the question is, would it show in the viewer which that like if you could give the point a different name or something? I don't know if that's currently possible.
No, not currently. It's in the to-do list. It has been asked by several users, I think. The only way of naming particular points for now is to use the labels, which you can rename with the F2 key.
Do the labels show up in the viewer, Daniel?
Yeah. Oh, you don't see the label?
I don't know, but if you have a label, does it show up in the CC viewer?
Oh yeah, of course.
Okay.
You got exactly the same result. I think it was yes. Here it's the same result in CC viewer.
Okay.
If you save the club and the labels in the same bin file.
Okay, I got you. Okay, we'll take one more question. If anyone else has another question, otherwise we will end the meeting. Okay, I don't see anything coming through right now. So Daniel, I want to say thank you very, very much for the presentation.
You're welcome.
I appreciate it. I think CloudCompare is a wonderful achievement, and the fact that you're making it available to everybody to use, I think is really, really excellent. And like I said, I'm very, very pleased with the way this has developed. Especially in the recent past, there's been a lot of changes, and I'm looking very much forward to see what else is coming from this particular product. So again, I want to thank everybody for attending. If you have any other questions for Daniel, he does have a regular, I'll just see if I put it in here. In the chat window, it's cloudcompare@danielgm.net. So you can email Daniel directly for any questions that haven't been responded to at the moment. And once again, I appreciate everybody's attendance, and thank you very, very, very much. Have a good day, everyone.
Thank you very much, Eugene, and thank you to all of you. And don't hesitate to visit the website and to send me emails, of course.
Okay. All right, bye-bye.